Dalimil, telling us about dispersive CFT sum rules. Okay, Dalimil, take it away.
That's right. Thanks for the introduction, Shuhank. Yeah, I'll talk about dispersive CFT sum rules, which is also the title of a paper that we recently wrote in collaboration with Simon, Leonardo, and David. And the talk is also partly based on an earlier paper that I wrote last year with Leonardo and Shinan. And please don't hesitate to interrupt me with questions at any time. I may be able to follow the chat, but it's probably better if you just unmute yourself and ask a question in a microphone. All right. So what is the broad motivation for the kind of things I'm going to explain later in the talk? So that there are roughly two related ideas, two possible motivations. The first one is that we would like to have an approach to the analytic bootstrap with rigorously bounded errors. So somehow to have an approach to the conformal bootstrap. By the way, in the rest of the talk, when I say bootstrap, I mean the conformal bootstrap. And I'll say more about what it is later. Yeah, so we would like to have an approach to the conformal bootstrap, which is simultaneously analytic and also rigorous. So in that sense, it's like a hybrid of it would be the hybrid of the numerical bootstrap and the analytic Lightcon bootstrap, so to say. So just to explain this a bit better, so in the bootstrap nowadays we have a sort of a paradoxical situation where the numerical approach is more rigorous than the analytic one right now. If you're doing numerical bootstrap at some finite number of derivatives, and then you find some exclusion in the parameter space of your CFT, then you know it's completely rigorous. There can never be a unitary CFT outside of those bounds. So that's a good thing about numerical bootstrap. It's completely rigorous, but unfortunately it's numerical. So it doesn't always give us the best insight into why those bounds are valid. On the other hand, the so-called analytic Lightcon bootstrap, or alternatively the Lorentzian inversion formula. So I may also, for the experts, if you're familiar with, I'm also going to use these interchangeably. That Lightcon bootstrap is basically equivalent to the inversion formula at the end of the day. So that part, it's nice because it's analytic. It gives you some nice analytic predictions for, say, double trace operators in your CFT, but it doesn't lead to a sort of controlled approximation. If you're working in the context, you never know how big your errors are, and that there is in principle no way to know. Essentially, it's because the sums that you find are usually asymptotic, and by including more and more terms, you're not eventually improving your precision. So for that reason, we would like to have an approach which is like a combination of both, which is both rigorous and analytic.
Dalimil, so there are also some other discussions on analytic bootstrap that use a lot of Tauberian theorem. And I thought those discussions are rigorous, right? But perhaps that's not.
That's right. Yeah, I should have. Thanks for mentioning that. Yeah, that's right. That is a nice approach, which is completely rigorous. It's an approach for studying the high energy spectrum. That works very well for that. And what I'm going to talk about today is more about the low energy, like the bounds on the lowest dimensions in the theory. So it's complementary.
Okay, thank you.
And the second motivation is probably more ambitious, and that's the hope to eventually systematically derive bounds on holographic CFTs. So it's somehow to have like a version of the numerical bootstrap which constrains large C or holographic theory. So the numerical bootstrap works extremely well for theories of small central charge, like the 3D Ising model, where if you work hard numerically, you can end up with a small island in the parameter space around the 3D Ising model, but we don't have anything like this at the moment to constrain holographic CFTs. So the kind of thing that you would like to do is to say parameterize your holographic CFTs by the EFT data, by your low energy Lagrangian, and maybe be able to rule out some seemingly consistent effective field theories in ADS using the bootstrap. So we currently don't have any example. Well, there are some simple examples like the positivity constraint on the partial phi to the 4 coupling and things like that. But one would like to have a very systematic approach akin to the numerical bootstrap, which like generalizes this partial phi to the 4 constraints in a broader sense. Okay, so those are the motivations, and I'm not quite going to resolve them, especially the second one in the talk, it's just to motivate. And the approach that I'll propose to attack these questions is to use exact sum rules on the OPE data, which suppress double twist operators. And this property of a sum rule that it suppresses double twist operators is called dispersive, or we call it dispersive in our paper. And that has to do with the fact that these sum rules come from dispersion relations, and I'll explain all of that later on. So for example, for the second part, the reason why is it important to suppress double twist operators? I mean, the reason is that the numerical bootstrap doesn't know a distinction between single trace and double trace operators. So for example, if and the thing that you really want to constrain in holographic CFTs is the spectrum of the single traces. Like the double traces sort of go along for the ride. But say if you have some numerical bootstrap bound, which is like an upper bound on the operator dimension, it can always be satisfied by a double trace operator. You don't know whether that's like whether the operator which satisfies it is double trace or single trace. So you haven't really learned much about the single trace spectrum. So for that reason, it's important to sort of get double traces out of the game and proceed from that.
Are you using double trace and double twist interchangeably?
Yes, I am. Yeah. Thanks. So are there any other questions about this slide? Okay, if not, then let's go on. So just to set the stage, in the rest of the talk, I will focus on a unitary CFT in a pretty much general number of dimensions, and I'm going to focus on the crossing properties of the 4-point function of identical scalars in the theory. So in a CFT, we can write it in this form, where there's some function of two cross ratios, z and z bar, with some conformal covariant prefactor. And the core of the bootstrap is the idea that we can expand this 4-point function in different ways using the OPE. So here is the expansion in the S channel. These G's, capital G is the conformal block, so the S channel conformal block. And we can also expand it in the T channel. And the S and T channel are related by some transformation. Z goes to 1 minus Z. But the technical details are not so important for what I'm going to say. And the sum runs over the primary operators in the theory. Importantly, there is this OP coefficient squared, which is a positive number in unitary theories. Okay, so the talk is about sum rules, and this is already a sum rule for every Z and Z bar. Well, for Z and Z bar in certain ranges, which is the range where both the S and T channel OP converge, you get a sum rule. So it's like a 2-parameter family of sum rules parameterized by complex numbers Z and Z bar. Or more generally, to get sum rules, you can consider functionals. So some functional omega, which acts on functions of Z and Z bar, sends them to numbers. And because this equation, okay, and you want to activate this function on the equation, and because the equation is symmetric under switching S and T channel, you can, without loss of generality, assume that the functional acts in an antisymmetric way. So somehow the most general constraint that you can derive from this equation is by acting with this crossing antisymmetric functional on the equation, and assuming the functional commutes with the OPE, that you can exchange action of omega and the sum over O, you arrive at this equation, which by itself is completely useless because I haven't really told you what omega is, but for every such omega, you get such an equation. And this is the sort of the most general OPE sum rule that you can get, and all of the sum rules which I'll discuss in this talk are of this form for some suitable omega. Okay, so that was just an overview of the foundations. Okay, so now let me say a few more general things about what kinds of omegas are constraining. Okay, as I already said, Bootstrap is essentially a search for, is the art of searching for very constraining omegas. And the key property is that these coefficients are positive, which also means that we want omegas with a nice positivity property. So in particular, imagine you found such an omega which is positive on all conformal blocks, just like on all conformal blocks of unitary operators, of unitary bounds. Then it would follow that there are no unitary CFTs. It would just follow that this equation can never be satisfied because the sum of positive numbers can never be 0. So we know that's definitely not true, ever. the reason is that there is always at least one solution to this equation, to the full crossing equation, which is mean field theory, which is also you can think of it as a theory of a free field in ADS. That theory, well, the OPE of such a field has only identity and the so-called double trace operators, which are labeled by their twist and spin, and their dimension is 2 delta phi plus 2n plus L. So yeah, you cannot find a function which is always positive, but somehow assuming this was the only solution to crossing, to unitary crossing, then the best case scenario would be that you could find a functional which is non-negative everywhere, but vanishes on the spectrum of mean field theory. So it would look like this. It would have zeros on all the twists corresponding to double trace operators for all the spins, all the even integer spins. And it would be, and because it needs to be non-negative everywhere else, these would have to be double or even order zeros. So if such a functional existed, it would mean that there is only one solution to crossing, and it's mean field theory with the delta phi. And that's actually a logical possibility in more than 6 dimensions. So there's a chance that there are no unitary interacting CFTs in more than 6 dimensions. And one possible way to prove it, which as far as I know is, I mean, I'm not sure if it's possible, but I don't see any, it's possible that you can prove it this way. I just haven't found such a functional. So one possible way to prove that there are no interacting CFTs in more than 6 dimensions is to exhibit such a functional. Maybe it exists, maybe it doesn't. And
but but in order to really show that, I guess it would be more rigorous and universal to look at the stress tensor OPE, right? Because here you assume from the beginning that there's a scalar operator, and then you look at this. Yeah.
I mean, if there is a stress tensor, there's also a scalar operator. It's OPE, like most I think. But yeah, you're right. So strictly speaking, this function would say that if it existed, it would mean that every scalar field with dimension delta phi acts like a free field. Its OPE is just mean field theory.
Right.
That's true. So actually, this can only work in a certain range of delta phi, because once delta phi is greater than twice the unitarity bound, there is at least 2 solutions, which is phi itself and phi squared operator. You could have a 4-point function of phi, 4-point function of phi squared, and they have a different spectrum. So this is only a logical possibility in some small range of delta phi. But it's just like a fun example. I don't want to dwell on it too much. And actually, such a functional exists in the infinite C limit of n equals 4 as CFT. So for n equals 4 as CFTs in 4 dimensions, there is a rigorous proof that the 4-point function has to be the disconnected correlator. And then it's an interesting question, how do you go from infinite C? But we haven't really worked out that much. Okay, so yeah, I think that this was just to say that we want functionals or summaries which are non-negative and have this nice structure of double zeros. And what is a dispersive sum rule? It's a sort of sum rule where this condition is slightly weakened. In general, this functional doesn't exist, but dispersive sum rules will exist. And let me just tell you what they are. And later on, I will connect it to dispersion relations. So maybe the talk is a little illogical because I'm talking about dispersive sum rules before telling you about dispersion relations, but I thought it was maybe more I mean, the discussion of dispersion relations is a bit technical, so I wanted to postpone it to later. Okay, so what is a dispersive sum rule? It's an omega which has the property that it has double zeros on all double traces above a certain fixed twist. So it doesn't have double zeros on all the double traces, but from some point, from some n onwards, it does. So these are just the conditions which say that there is a double zero. And the functional action, so if I plot the action of the functional on conformal blocks, it would look something like this. I mean, it does something random for small values of the twist, and then eventually it has double zeros on all twists. Now it is not part of the definition that it has to be positive from this point on, but in practice, the most constraining examples of such sum rules would have some positivity condition, but it's not yeah, it's not a part of the definition for now, the positivity, just the structure of double zeros. Is the definition clear? Like in a sense, it's like you want to restrict to the space of some, like, in the numerical bootstrap, we restrict to a certain space of sum rules, which is like finite combinations of derivatives around the crossing symmetric point. These are not dispersive sum rules, but instead, like, I'm proposing to focus on this set of sum rules and work in that space to find bootstrap constraints. So these kind of things were discussed first in 1D, and then we also applied them to the modular bootstrap with Tom and Leonardo, and we found that these 1D functionals in the context of modular bootstrap actually provide an analytic solution of the sphere packing problem in 8 and 24 dimensions, which is, I mean, there's sort of a map between those dispersive sum rules and the proof due to Vyazovska and other people that the E8 and the Leech lattice in 8 and 24 are the optimal lattice, the optimal packings in 8 and 24 dimensions. So maybe that's a reason to, to study these sum rules further. And there were also some other works exploring such sum rules, for example, in DCFT, and also recently a Princeton group studied them in a context of CFTs on the real projective space.
Dalimil, just to clarify, in the modular bootstrap, the horizontal axis is delta, right? It's not the twist.
Oh, yeah, that's right. I mean, well, so far the way they've been applied to modular bootstrap is that there is no spin, it's just a spinless case. Right.
Okay.
So there is no distinction between twist and delta in that case. I mean, it's delta. Yeah, you're right.
Okay, thank you.
Any other questions? Okay, so let me now tell you a little bit why such sum rules are useful for holography. And this idea was sketched a little in a recent paper by Dean, Joao, and Sasha, and it's a subject of some ongoing work. So again, it's important that the contribution of approximate double traces is suppressed. And what does this mean? So let's imagine a 4-point function in a holographic CFT. So what do I mean by a holographic CFT? It just means consider some one-parameter family of solutions to crossing, solutions to this bootstrap equation, parameterized by central charge. So the parameter is a central charge, which becomes arbitrarily large. And in the limit where C goes to infinity, I just find disconnected, just the disconnected correlator. So there are actually two parameters. Well, there is C is the parameter, and then there is some large quantity called delta gap, such that below delta gap, the spectrum is very simple. It's just the spectrum of there's identity, and there are the double traces and multi-traces and so on, and maybe some finite number of low-lying fields. Like basically everything which you can see in the effective field theory is below delta gap. And they're above delta gap, it can be arbitrarily complicated. And as a function of as a function of C, well, at infinite C, we just have identity and the double traces, and that at higher order sim1 over C, these double traces are corrected. They acquire some anomalous dimensions and anomalous OP coefficients, and also at order 1 over C, these new single traces appear. And at higher and higher order sim1 over C, you get higher corrections. So now we have this, and we consider the crossing equation for that OPE. And we apply some dispersive sum rules, some dispersive functional omega, which is the property that it has double zeros everywhere above delta gap. So somehow this property that it has double zeros above delta gap ensures that we can cleanly separate the low energy contributions and the high energy contributions to the sum rule. So let's put the low energy, the light contributions, those above delta gap to one side, and the heavy contributions to the other side. These low energy contributions are completely computable if you know the EFT. Well, first of all, I should say that at the leading order, so at order 1 over c to the 0, the sum rule is trivially satisfied because, well, okay, I don't maybe want to go into details on that, but the leading order of the sum rule happens at order 1 over c, which is where there's some interesting physics, like you can see the EFT spectrum. So the left-hand side is computable if you know the spectrum of single trace operators and you know the contact diagrams or the low energy Lagrangian. And the high energy spectrum can be arbitrarily complicated, but suppose that we have an omega which is sign uniform on heavy operators. So for sufficiently large delta, for sufficiently large delta gap, this has a, for example, this is positive. Well, then this equation imposes an inequality on the EFT, like it's some inequality on the low energy data. For example, the constraint that partial phi to the 4 coupling for massless scalar in ADS needs to be positive can be derived using this logic, but it generalizes. There's a whole infinite family of such sum rules that constrains the low energy EFT. So in other words, it's this kind of logic constrains the low energy EFT from the fact that we have UV completeness, and it kind of balances the light and heavy operator. So for example, if you just take the exchange of gravitons on the left-hand side is non-zero. It tells you that there has to be some UV completion, and it tells you some concrete predictions for what the UV completion needs to be in order for the theory to be consistent. Okay, any questions about this slide? Okay, so I haven't really told you where these things come from. So that's what the rest of the talk will be about. And one nice thing that happens is that there are many different approaches, and they all lead to the same structure, to the structure of these double zero-like sum rules. As I already said, you can think of them as some functionals applied to the crossing equation. So that shows that they are not nice, they are rigorous and exact, but fundamentally they come from dispersion relations. So recently there was a dispersion relation derived in position space for position space correlators by Dean Carmey and Simon Caron-Watt. There was also a related work, well, there was also work in Mellin space where they considered dispersion relations in Mellin space and imposed the so-called Polyakov condition. That was due to Joao, Xiao, and Sasha. And so one of the things we did in our paper is that we showed that these two dispersion relations are completely equivalent. And finally, there seems to be a connection to these superconvergence sum rules. So superconvergence sum rules are, well, I won't have a chance to discuss them in more detail, but they are, I mean, there are sum rules coming from the commutation, from the fact that space-like separated light ray operators commute with each other under certain circumstances. And anyway, all these four approaches seem to basically lead to the same idea. And physically, this the sum rules really come from causality, or more generally consistency in Lorentzian signature. So essentially, the reason that dispersion relations are valid is thanks to analyticity of the correlator. And analyticity, complex analyticity, is a manifestation of causality of the underlying theory. So the causality constraints were, in the context of S matrix and CFTs, were studied by many beautiful papers. So here's a selection of a few of them. But yeah, so now I'll tell you a little bit about the dispersion relation in position space. So I won't have time to discuss all these interrelationships. So let me just focus on this vertex, on how.
I have a question. Maybe you said it, but I missed it. You defined dispersive sum rules before, saying that it should vanish on the double zeros, and this to me seems like a different definition. Are they related?
Well, I have, yeah, I haven't really, yeah, I think I'll address this. I'll explain how what I defined before comes from dispersion relations.
Oh, perfect. Thank you.
That's the point of the rest of the
That
talk.
was
Yeah, I mean, as I said, it's maybe the talk should be structured in the opposite way, but I chose it first, give a definition and then say how
okay.
Yeah. Okay. Okay. So. Right. So let me say a few words about dispersion relations in CFTs. The idea of dispersion relations is to derive the dynamics from, roughly speaking, the absorptive physics. And in front of us, you could say that they allow you to derive the amplitude, for example, the S matrix or the CFT correlator, from some simpler quantity, which is the discontinuity of the amplitude. So in some, like in a toy example of a dispersion relation would be, say, if you have a function of one complex variable with a pair of branch cuts, then you can evaluate the function and assuming that it's analytic everywhere, and also assuming that it has some decay at infinity. Then you can evaluate the function at the point using the Cauchy integral formula. So just with the kernel 1 over z minus z prime at this point. And then thanks to the analyticity and boundedness at infinity, you can pull the contour to the branch cuts to arrive at a discontinuity. So this kind of contour just computes the discontinuity of the quantity across the branch cuts. And in this way, you have expressed the value of the function at any point in the complex plane as an integral of the two discontinuities. So it allows you to recover the amplitude from the discontinuity. Recently, there was a pair of papers, mostly the first one by Dean and Simon, that constructed such a dispersion relation for the 4-point function in a CFT. So in that case, it's a slightly more complicated situation because we have not just one complex variable, but two. There are two cross ratios, z and z bar, and we should think of both of them as being complex. So there are two independent complex variables, and in each of these variables, the structure looks like this. So there is a branch cut starting at 0, which is sort of the S-channel branch cut. And there's a branch cut starting at 1, going to infinity, and that's the T-channel branch cut. And there's also a natural analog of the discontinuity, which is the double discontinuity. And physically, this is a double commutator. So the S-channel the double discontinuity S-channel, denoted disk S, is a double commutator like this, 1, 2, and 3, 4. And there's also a T-channel double discontinuity, which is just a different ordering of operators. It's 1, 4, and 2, 3. So what this dispersion relation of Karmian-Karnow does is that it reconstructs the full 4-point function as a function of z and z bar from the double discontinuities evaluated in this Lorentzian kinematics. So when you're sitting on the branch cuts, you're in Lorentzian kinematics with some independent real z and z bar. In other words, well, what this means is that one can write, these people show that you can write the 4-point function as a sum of two terms. One is the contribution of the S channel. The other one is the contribution of the T channel. And the S channel part is some integral of the S channel double discontinuity with some specific kernel. And they found this kernel. This kernel is some relatively complicated looking function involving the elliptic, some elliptic function, which you can write as a 2f1. Yeah, so what else can I say? Right, so this kernel depends on 4 variables because the 4-point function is a function of 2 variables, and you need to integrate over 2 of them. So there are 2 integrated ones and 2 free variables, and this kernel is a complicated function of the 4 variables. And the additional part is obtained by crossing symmetry. So in a crossing symmetry correlator, the GT and GS are just related to each other by crossing symmetry. So basically, this is a theorem in complex analysis. It's a completely rigorous theorem about all functions which have some physical properties like boundedness at infinity. So in this case, infinity is the U channel. You know, S channel sits here, T channel sits here, and U channel is at infinity. So in order to derive this dispersion relation, we need to know something about the U channel behavior, and both in the U channel OP limit and the Regge limit, but in both cases there are some bounds which come from unitarity. So there's a bound on the Regge behavior. The Regge limit is bounded by the OP limit thanks to unitarity. And that means that we can drop the arc at infinity, so to say. So that's nice. There's a nice dispersion relation for the correlator. What conclusions can we draw from it? So one thing that you can derive rigorously is what we called Polycophage expansion in our paper, and that's that just comes from expanding the S and T channel part using the OPEs. So remember that the GS comes from the S channel double discontinuity by acting with the kernel, and GT similar from the T channel double discontinuity. So that means that we can reliably compute GS using the S channel OPE and also compute GT from the T channel OPE, because this D-disk S is can be computed using S channel OPE. That's just from the definition here that you can expand this commutator using the S channel OPE. And what you find is the following. Well, you find that the 4-point function is just a sum over all the primaries in the OPE of the sum of two objects. One is comes from the S channel, comes from T channel, and this is P object, which is just the dispersive transform of individual conformal blocks. So you can ask what are these objects, and actually they are quite simple. They just turn out to be Witten exchange diagrams. So even though from the start we didn't assume there was an ADS, just from the kinematics, from the general conformal dispersion relation, these objects appeared. We call them Polycophage blocks, and you can actually fix these objects even without knowing exactly what this kernel is, just from some basic principles. So here are the basic principles which follow from the structural dispersion relation, which uniquely fix these Polycophage blocks. So first of all, in the S channel, they have the same D-disk as the individual conformal blocks. And in the T channel, they have a vanishing D-disk. So this just means that, this just says that the S channel D-disk of the left-hand side is completely captured by the S channel D-disk here. So the S channel D-disk of GT is 0, and the T channel D-disk of GS is 0. So there is this nice split of D-disks underlying this equation. And at the same time, they have good Regge behavior in the U channel. So what this means is that you can write the S channel Polycophage block as the conformal block plus some double trace terms. These are just double trace conformal blocks and their derivatives. So these are the objects whose D-disk vanishes. So if I take the D-disk as of this equation, I find only D-disk of the first term on the left-hand side, and D-disk of everything else drops out. And if I take the T channel D-disk here, well, I just get 0 because they're only double trace. So this is precisely the OP structure of Witten exchange diagrams. So this is like an S channel exchange Witten diagram. And the requirement of good Regge behavior in the U channel completely fixes the contact term ambiguity. It was also discussed in a recent paper by Charlotte and Massimo. So in other words, what the dispersion relation shows is that you can always expand the 4-point function as a sum of S and T channel exchange Witten diagrams. Okay, now the final step to deriving the dispersive sum rules from dispersion relation is to just compare this expansion, the Polycophage expansion, to the usual OPE. So we have the correlator, which we can expand using the Euclidean OPE. And we can also expand it using the Polycophage blocks as follows from the dispersion relation. So this is now a family of sum rules parameterized by Z and Z bar. So it's some reformulation of the original crossing equation. So the original crossing equation has S channel OP on one side and T channel OP on the other side. So it's quite a different equation. But you can derive this equation either by the route that I followed through dispersion relation, or you can sort of use it to reconstruct the functional that you would need to act with on the crossing equation to derive this equation. So there are two equivalent ways of thinking about it. But what you can do now is that you can expand this equation at small z. So that's something that's not allowed for the usual crossing equation. If you expand the usual crossing equation at small z, the S channel is fine because it converges, but the T channel is not fine because it stops converging at z equals 0. But this equation actually is valid. I don't have a good physical reason why, but it just follows from the math. Is there a good reason? Yeah, you can prove that you can just expand this equation at small z, and what you find is that the equation just becomes equivalent to the statement that the extra double trace contributions to these objects cancel out. So remember that the PS here on the previous slide had the S channel single trace block and also some double trace blocks. So the single trace block is the same on both sides. So it just cancels out, and what is left on the right-hand side are the double trace blocks. So essentially, for each double trace block, there is one sum rule. So well, essentially, you can label the independent sum rules following from this equation by N and L, which are labeled with double traces, and there are also two kinds of terms. There is the term of the conformal block and the term of the derivative of the conformal block. So that's why there are these alphas and beta sum rules. So these alphas and beta sum rules they're a basis for unsubtracted dispersive sum rules. Okay, then. Yeah, so this maybe not be entirely, maybe this is not entirely obvious, but the alphas and betas are dispersive. So they have double zeros on double traces, and that's essentially because if you remember the definition of the Polyakov-Regge block here, it comes from the double discontinuity of the correlator, and the double discontinuity produces the necessary double zero. So essentially, the property of being dispersive comes from the structure of a double commutator, which produces the double zeros for you. And by sort of increasing, well, okay, I didn't write this on the slide. Maybe I should, but this for example, this beta and L is a sum rule that has double zeros everywhere except for the N and L double trace conformal block, where it has a simple zero. So these are like the elementary dispersive sum rules, which you can take linear combinations of to produce more complicated sum rules. Also, one point which I didn't really mention is the need for subtractions. Okay, maybe I can discuss that later. Well, it's essentially these sum rules alpha and beta are not individually valid, and that's because the Regge behavior of correlators is not as good as you would want in the U-channel Regge limit, and to get a valid sum rule, you need to consider some linear combinations, some simple finite linear combinations of these objects. That's what the word unsubtracted means. We need to use subtractions to derive valid sum rules. Okay, so now to to finally give you something more concrete is let's see what happens if we work with the dispersion relation at the leading order. So at leading order, it's small u. So we take u, the limit u going to 0 in this formula. So z goes to 0 at fixed z bar. So in other words, it's small u at fixed v. Well, what you find is a one parameter family of dispersive summaries, which is parameterized by the cross ratio v. And they all have double zeros on all the double traces above leading twist. So these summaries are non-vanishing on the leading twist trajectory. That's related to the fact that we use the subtractions, but some technical detail that I guess we don't have to worry about now. But there are double zeros on all the higher twist double trace blocks. And you can actually write down a closed formula for the action of the sum rule on conformal blocks. It's some double integral over the two cross ratios, u prime and v prime. So it's parameterized by v. For every v, we have a sum rule, and we are integrating over u prime and v prime over some Lorentzian region. And there's a kernel, which is always positive in this region, times the d disk of the conformal block. So this is exactly the structure which produces what we want. The double zeros come from the double discontinuity, and the non-negativity comes from this kernel being non-negative, and also the conformal blocks being non-negative in the Lorentzian signature. So we find that not only there are these nice double zeros above leading twist, but also the sum rule is non-negative as long as delta is above 2 delta phi. So something that we noticed quite late when we were writing the paper, so we don't really understand it fully yet, is that actually this sum rule is equivalent. The sum rule following from this BV is equivalent to a version of a superconvergence sum rule. So superconvergence sum rules are statements that space-like separated light ray operators commute. So we have this kind of situation where we create some state with a operator phi, then we have two null integrated operators, and then we have a outstate phi. And assuming these light ray operators are always space-like, and assuming some suitable condition at infinity, this is 0. Actually, this condition at infinity is a bit subtle, and it's not quite satisfied unless you rescale the correlator. So the reason for this v prime minus u prime over u prime v prime is that we need to UV improve this. Well, UV in the sense of high energy. This is sort of a subtraction which makes the correlator softer in the U channel Regge limit by 2 units of spin, and that makes this equation valid. Okay. Okay. Now let me finally tell you a few applications of this sum rule. So we start from the sum rule dv, which is valid for all identical scalar correlators. So this sum rule, as I said, has double zeros on subleading twists, but it's not vanishing on the leading twist. And we would like to make it vanish also on the leading twist. Why? If you do that, then you find an extremal functional for the twist gap problem. So it is expected that, suppose you ask the following question. Suppose you ask, what is the maximal twist gap of spinning operators in this in the 4-point function of identical scalars? The answer should be 2 delta phi. Well, that's because there is definitely a correlator with the twist gap, which is just mean field theory, and also corrections to double twist operators and leading trajectory are negative. The anomalous dimensions are negative, as follows from the Lycon bootstrap or the inversion formula. So we expect to be able to prove that there needs to be an operator with non-zero spin, and twist less than 2 delta phi. So one way that it would follow is if we can construct this kind of functional. A functional that has a negative region above, sorry, below 2 delta phi and is non-negative above. And this B of E is quite close to it, but what we need to do is, well, we need to sort of apply some projection to kill the values on the leading twists. So on the leading twist, this guy was non-zero, and we have to make it, we can make it vanish by essentially anti-symmetrizing under swapping T and U channel. If you do that, and if in addition you just take the V derivative of that, you find exactly the right structure. So the claim is that this sum rule proves that there must exist a primary with twist less than or equal to 2 delta phi and spin, which is some positive even integer. And this generalizes a result due to these gentlemen that who constructed such a functional using balance space for a certain range of delta phi. So that their construction works only if delta phi is between the unitarity bound and some finite multiple of unitary bound, but it seems like this position space approach of BV gives you such a sum rule for general value of delta phi. Okay, do you have any questions about that so far?
So here you're talking about holographic CFTs, or right?
No, this is general.
Or is general?
General, yeah.
But then but then there are corrections to double twist. How do you know where exactly the double twist operators are that you say that the functional vanishes? Well,
you don't know exactly where they are. It's just that this functional proves that there has to be at least one operator in this region, in the region between unitarity bound and 2 delta phi. I mean, it's a relatively simple result which you could have guessed anyway from the inversion formula. It's just a statement that leading twist anomalous dimensions of spinning operators are negative. Yes, so I mean, all the other operators would be somewhere in the positive region. So to make the sum rule valid, there has to be at least one in the negative region.
Okay.
So from these results for large J, right?
Mm-hmm.
You can derive that also the anomalous dimension is negative.
Yeah, that's right.
Now this is similar, but for finite J.
That's right. It's for finite J, and it's a different approach to the same problem. Maybe this approach is more satisfying because it's more along the lines of the numerical bootstrap. If you try to address this question with numerical bootstrap, it basically will be a question: try to maximize the gap in the twist sector. The numerical bootstrap would come up with some function like this. And there are some subtle differences between how the icon bootstrap works and how this kind of logic works. Essentially, now you can also use this sum rule to actually get a formula for the anomalous dimension, because there needs to be some detailed balance between the contribution of the double trace operator and the contribution of all the other operators in the theory. So you would get a convergent sum for the anomalous dimension as a sum over all the other operators. And that's something that the inversion formula doesn't give you. If the inversion formula will tell you that it will tell you what is sort of the contribution of a fixed cross-channel operator to the anomalous dimension in the S channel. But if you try to sum over all the operators in the T channel, you would get infinity. The series is sort of asymptotic. But here it's a nice convergent sum. So it's in that sense, it's an improvement over the large J star.
Sorry, I have a question. So when you say that for example, if you go to the statement that the anomalous dimensions large spin are negative, this functional doesn't quite prove this, right? Because all it says that there should be at least one operator below the double twist line. So
yes,
if you have like a scalar, well, maybe not scalar, but like if you have one operator which has negative anomalous dimension, then you cannot say anything about the other operators anymore, right? It just says that there should be one operator.
That's right. Yeah. So yeah, I'll come to this in the next slide.
Okay. When you say that you can, sorry, I was just going to ask, when you say that you can compute the anomalous dimensions when you're in the right formula, you can compute the anomalous dimensions weighted by OP coefficients always.
Yeah, that's right. Yeah. That's right.
So extracting just the anomalous dimension by itself is a bit,
Yes.
is some additional task, right?
Yes. Yeah, that's true.
Okay, thanks.
Yeah. So as Per somehow hinted, or as also the analytic Lycon bootstrap hints, there is a stronger claim to be made, which is not just that there is at least one primary operator below 2 delta phi, but actually for each individual spin, for each non-zero spin, the optimal upper bound on the twist gap should be saturated by mean field theory. And this was actually noticed already in the classic solving the 3D Ising model paper, where most famously they were looking at the upper bound on the dimension gap in the scalar sector. So they have this plot where they don't impose any restrictions in the spinning sectors. So in spinning sectors there can be anything above unitary bound, but in the scalar sector they impose a gap and they find that some exclusion above a certain curve which is a kink, and the 3D Ising model sits at the kink. But then they also repeated the same task in higher spin sectors. So now not assuming anything about scalar spectrum, just assuming that there is a gap at spin 2 or spin 4. No. And what they found is that the optimal upper bound is just saturated by mean field theory. Just the twist gap is 2 delta phi, it's a straight line. And it would be nice to prove this analytically. Their proof is sort of numerical, and it hasn't quite converged. You need to work at finite number of derivatives. So for various reasons, it would be nice to prove this analytically. Again, you can say it sort of follows trivially from the Lycon bootstrap because at large J, the anomalous dimensions are negative, but this would be some finite J result of this function summary form. And we managed to do it in some very limited range. So we using this superconvergence summary BV, because there is this extra parameter V, you can use it to impose additional double zeros on the other operator, on the spinning operators. So basically you want to trade the V label for the J label. And when you do it for spin J, it turns out that the resulting sum rule does the job. So it has the right positivity properties to show that in a certain range of delta phi, we get this extrema function, that we prove that there has to be an operator for spin 2, not for any spin, just for spin 2, below 2 delta phi. And there's also some interesting evidence that the numerical bootstrap doesn't lead to a unique functional. So there's actually a non-trivial family of sum rules which prove the same thing. That's kind of interesting. I think the law used to be that for every point on the bound, there is a unique functional which does the job, but at least for this mean field theory problem, it looks like there is a non-trivial family of sum rules which prove the same thing. I mean, we didn't really say anything about a 3D Ising model function. Probably in that case, there is a unique object because it needs to know about the entire spectrum of the theory, assuming the 3D Ising model saturates it. So, sorry, are there any questions about this? Okay, finally, now we took this sum rule, so the sum rule which has double zeros everywhere except for the spin 2 leading to its double trace operator, and we just tested it in the 3D Ising model. Concretely on the 4-point function of sigmas, where there's quite a lot of OP data known about this 4-point function thanks to some nice numerical work of David Simon-Staffen. So we can actually just plug in the contributions of the OP to the sum rule and see what we get. First of all, the only operator which gives a negative contribution is the stress tensor. So let's normalize the contribution of the stress tensor to the sum rule to be -1. And the validity of the sum rule is that everything else needs to add up to +1. And nice thing is that all the other operators are in a positive region, so they all contribute positively. So there's both a lower and upper bound on the total contribution of the rest of the operators. And if you include just 3 of them, just the epsilon operator, which is a scalar, and the next scalar operator called epsilon prime, and if you also include the epsilon gives like 95%, epsilon prime gives additional 2%, and then t primed, which is the next spin 2 operator, gives another 1%. So just from including these very simple set of operators, you already satisfy the sum rule to 98% accuracy. So it tells you that everything else needs to contribute as 2%. In other words, the sum rule gives an approximate identity satisfied by the low energy data of the 3D Ising model. So it's you can imagine that by using several such sum rules, maybe this one and a couple of other sum rules, you could find an approximate analytic solution to the 3D Ising model just by leaving the parameters of t, central charge, delta epsilon, delta sigma as free parameters, and try to impose these sum rules and see where you can fix these parameters to some good accuracy. So the reason this is a little bit successful is because of double zeros. That all there are of course double twist operators which are close to the double zeros, and that's why they contribute very little. And also all the other operators must have very small OP coefficients. Okay, so that's it. Let me just quickly summarize. Hopefully I convinced you that there is a large set of interesting OP sum rules which arise from the conformal dispersion relations. What I didn't really have a chance to explain is that they provide sort of a bridge between different approaches. There was this approach using Polyakov blocks, using Mellin space, position space. It nicely ties the analytic to the numerical bootstrap. But it's still largely unexplored. Like we literally only looked at the consequences of the underlying sum rules. And for example, there was a recent work by the EPFL group, which applied the dispersive sum rules to the epsilon expansion and also some within diagram computation. So for example, they were able to reproduce essentially all the data about the Wilson-Fisher fixed point up to order epsilon to the 4, and even made some new predictions using this. So basically, this approach is at least as powerful as the inversion formula, but it has some improvement over the inversion formula. There is a lot to be done. Something that we are currently working on is bounds on holographic CFTs. Then it would be nice to understand more precisely the connection to superconvergence, generalize to external operators, to generalize to other sets of external operators, which may plausibly lead to solving there's an important problem in holographic CFTs, which is to show that this A minus C over C for the 3-point functions of the stress tensor are bounded by 1 over delta gap squared with some constant here. So it'd be nice to actually prove something about this constant. To find the value of the constant which makes this equation valid. And finally, it would be good to try to use it in numerics. So numerical bootstrap works very well with the standard, well, it works pretty well with the standard basis of derivatives at the crossing symmetric point, but it requires high precision if you want to improve your result just a little bit. So maybe by using some rules which are closer to, which know more about the analytics in the Lorentzian signature could improve the performance of the numerics. Okay, that's all. Thank you.
Right. Any more questions?
Some time ago, there was some rule by Marcus Luthi and others. I don't remember the details, but I think it was saying something like the central charge is equal to some sum over single trace operators. That's the spirit similar to this. You think well, first of all, is that true, or can it be proven or disproven using this method?
I think it can be proven. I think. I mean, I'm not sure if exactly their sum rule can be proven, but if you, for example, look at this this sum rule, well, the stress tensor is the only contribution which is negative, so you can put it sort of on one side, and then all the double traces are suppressed by the double zeros, so they will go like 1 over. So the stress tensor would go like 1 over c,
right?
And all the double traces would go like 1 over c squared. So it gives a leading order in 1 over c. It gives you central charge, or 1 over c is some sum over contribution of anything which is not a double trace.
I see. So in a case where, for example, the string scale is variable, like ADS5, then the left-hand side would be independent of lambda, for example.
Yeah, that's true. Yeah, the left-hand side.
Yeah. Summing, yeah, I think I find them interesting because you would be summing over in the right-hand side over a bunch of things that are all, I mean, naively very suppressed because it's they're very high dimension operators. But there should be some enhancement so that it gives you in the end some answer which is different from independent of lambda.
Yeah. So one general feature of these dispersive sum rules is that there's an important distinction between them. Just using the crossing equation. In the crossing equation, the contribution of high dimension high interest operators is exponentially suppressed. It converges exponentially fast, but in these dispersive sum rules, it's actually it's a power law. So the contribution of some heavy operators goes like essentially 1 over twist or 1 over delta gap to some power. That's related to the fact that, I mean, if you think about these sum rules as arising from the crossing equation, by integrating the crossing equation, there are parts of the integration region which sort of touch the boundary of convergence of the OPE. So the OP converges exponentially fast, but the exponent becomes very small once one OP stops converging. So these sum rules sort of explore the whole. They become very close to the part where the OP doesn't converge, and that's sort of what changes the exponential decay of the tails to a power law decay of the tails.
Yeah, I guess it's power, but still should have this property that for large lambda, each individual term is very small, but the whole sum is independent of lambda.
Yeah, exactly. It has to be true. I mean, we tested this in n equals 4 super-rank mills at small lambda. So you can test it perturbatively around lambda equals 0, and it works order by order in lambda.
I see.
But of course, strictly at infinite lambda, you get a contradiction because infinite lambda, there is naively nothing in the string sector. But that's related to the fact that at infinite lambda, the Regge intercept becomes 2. So all of these sum rules assume that the Regge intercept is strictly below 2.
Can you apply this to, well, this is another, well, maybe I should let other people ask questions.
No, you can ask.
What if you have the standard model in ADS? Is there something that, some rule that tells you?
Yeah, it better be valid. Yes, so
I guess the rules that don't tell you that there should be some state below some scale, right? So imagine you had a just the theory of pure gravity, or it's just that there are no other single trace operators. Is that in contradiction with the sum rule, or there could be some contribution at the Planck scale, which?
Yeah, there has to be a contribution from the Planck scale. Like the sum rules can tell you what exactly it has to be at it. If you have a theory of just a scalar particle and a graviton, then the contribution of gravity to the sum rule is non-zero. So there has to be something else. So this gives you some weakish constraints on what the something else has to be. Right? It can be at the Planck scale. I mean, the nice situation would be if you could actually prove something about the low line contributions without assuming anything except for unitarity above the heavy contributions, like in this sum rule where it's like, you know, the graviton would be on the left and the Planck scale would be on the right. Mm-hmm. They can always be balanced, but if you know, if you can make sure that the contribution of the Planck scale is sign definite, then you can prove some inequalities above the light operators. Mm-hmm. But we haven't really applied it to the standard model yet. Maybe that's something to try.
Well, if you can always obey the sum rule by adding some extra stuff at the Planck scale, it's not obvious. It will give you something.
Yeah, yeah. Well, right there. I mean, the point is there's more than just one such sum rule. So sort of by ranging through different sum rules, maybe you could hope to cancel out the contribution on the right hand side or something, or you take some differences. Yeah.
There's the idea that wherever you added the Planck scale will make the theory completely finite also, because you don't really want the UV divergences in ADS, right?
Mm-hmm. Sorry, I'm not sure if I understand, Igor. I mean, as opposed to flat space?
Yeah, I thought to really have a good ADS CFT duality, you want a UV finite theory in ADS.
Yeah. I mean, here we are assuming that we have like a standard unitary CFT on the boundary, which is like UV complete.
Igor, by UV finite, do you mean that
there are no, there are no short distance divergences in the bulk theory, right?
But if you had something like M theory, I mean, 11-dimensional supergravity, you have such short distance diversion.
Well, in string theory, you don't, right?
In string theory, you don't. Yeah, but we have the example. Yeah, so we have the example of M theory where you do, and we think that they are okay ADS CFT duals. I mean, of course, in the full theory they should.
Yeah, in the full theory, I thought they should cancel because.
Yeah, but nominally in the gravity theory, you have them, right?
Yeah, I'm not sure how to really interpret them from the bulk theory point of view, from the boundary theory point of view.
Well, as you said, in the full boundary theory, they are not there, but it's some physics that goes beyond the gravity theory.
Right. That's why I was asking if some Planck scale effects are assumed to cancel divergences, sort of like in strings.
Ah, okay, yes.
Yep. Well, if I understand the question right, you're asking whether this would be also valid, for example, in the M theory case. I think it would. I mean, it really only works. It only one assumes that you have some sequence of finite C theories with ever increasing central charge, which in a sense it's like non-perturbative in C, but then we are expanding everything at large central charge at the end of the day. So even for the M theory like ADS CFT duals, this would still be true. So basically the sum of the UV would have to give you something of order 1/c, even though maybe the individual terms don't look like they go like 1/c.
Mm-hmm.
Is that what that's kind of what happened? what happens in M theory, like that there are some these strange powers of 1 over C, right?
Dalimil, when you showed those previous statement that there has to be some operator with twist below certain bound, those statement uses some assumption or property of the sign for this functional at large delta.
The statement here on this slide, for example.
For example, yeah.
I mean, it uses just what you can see in this plot. So the plot shows that.
But you showed, but you are certain that the value of B never turns negative.
Oh,
or,
you mean if I increase tau?
That's right.
Oh yeah, okay, yeah, great, yeah, very good question. Yes, well, I think in this case we actually didn't rigorously prove it, but we can prove it asymptotically at large tau, and then we can sort of plot it for small enough tau, and then by assuming that nothing crazy happens for intermediate values of tau, one could so we can prove it for this B of V, but this is the VV is not quite what we use. Like you need to take this difference, and this difference could in principle introduce some negative regions, but actually it doesn't. And that's something that I guess at the moment needs to be checked by hand for like individual. One nice thing is that it's enough to check it in 2 dimensions, because the higher dimensional conformal blocks can be expanded in the 2-dimensional conformal blocks with positive coefficients. So if you prove it in 2 dimensions, you prove it in all dimensions.
I see.
But yeah, it's a good it's an important loophole that needs to be checked.
Donald, do I understand correctly that like all the reasonable functionals that you can construct would always be analytic functions of delta? Oh, basically my question is sort of, if you were very ambitious, I guess you don't expect to be able to construct the functional which just plain vanishes above certain twist, let's say. So you cannot, because you expect to have functionals which are analytic functions in delta, you don't expect to be able to construct one which would vanish identically, say above delta equals 10.
Good question. I don't know any examples. In practice, these summaries, there are some integrals of conformal blocks. For fixed Z and Z bar, the conformal block is analytic in delta, and so the non-analyticity would have to come from some boundary regions of the integration, I guess. So if you set Z equal to 0, then the conformal block is no longer an analytic function of delta. Z equals 0 is some boundary region.
Oh, I guess it would have to be something like if you take the derivative of the conformal block with respect to delta, then the integral stops converging.
But we do have examples which are non-analytic in spin. Well, that's maybe that's a bit imprecise. But for example, there are examples of these functionals which vanish on all scalar operators and are non-vanishing for higher spin operators.
Okay, this doesn't contradict the noticed in spin because it's okay to finish it early.
Yeah, it's like you can have a sign. You can have a sign pi j or.
Oh, actually, since you have this functionals, do you understand what happens to them in between for non-integer j?
Well, so the zeros move with twist. The zeros are just a function of twist. So they move linearly, sort of. If you, I mean, the dependence on delta and j is there's a prefactor which looks like sine squared of pi over 2 times delta minus j minus 2 delta phi. So as you change J, the double zeros are going to move linearly.
So they remain double zeros.
Yes, yeah, yeah.
Okay.
In this case. But for the 3 Ising model, it could be something much crazier.
Yes, sorry, just a quick comment. Maybe I didn't make myself clear, but for example, if you look at gravity in ADS4, just pure gravity, and try to compute correction to vacuum energy from just free gravitons, then you have a UV divergence proportional to log lambda. But if you take, say, Vasilyev's theory with all the higher spin fields, you actually find that this one loop divergence cancels when you sum over all spins.
Mm-hmm.
And that's sort of necessary for consistency of the dual of the ON model in the boundary. So I think the same thing should happen in, for example, in M theory examples. That when you really sum up all this stuff, like all the KK modes, you should find that there is no log lambda in. I mean, it's a little different between even and odd dimensional ADS spaces, but for even dimensional, it seems important.
Mm-hmm.
Just to explain what I was trying to say. But.
Yeah, I understand. Yeah, thanks.
All right. Well, if there's no more question, let's thank Dalimil again.